All right, this is low budget optimization problems. Take two. Take one, couldn't post to Facebook. Take two, the dog's in front of, so good luck with that. I, unfortunately, am unable to be there today because I'm on my way to Indianapolis. However, I am not driving, so if you need to text me, please feel free to do so. Today, we're going to talk about our second type of derivative story problems. Our first type, those related rates problems, like how fast is the bottom of the ladder moving away as the top is sliding down the wall. Those are the ones we've already done. Today, we're going to look at things like if Farmer Fred wants to fence his pasture for his sheep and he has 120 feet of fencing, what is the most area he can enclose? So the problems we're going to be looking at today are going to say things like the fastest, the heaviest, the slowest, the strongest. These terms often are referring to extreme values like the maximum or the minimum. Think about that, maximum and minimum. We've been doing all along here with our derivatives, finding the max and the min. So these type of problems are called optimization problems. I have an example here, but the dog is in front of it. So just a minute, let's pick it up. Move the problem there. Sorry about the dog. She just wants to be in the video. So let's say that the traffic is moving through an intersection as described by the equation t at time t equals t over 0.1 t squared plus 10 in hundreds of cars per hour, where t is the time since 12 a.m. Find when the traffic is the heaviest. So they want to know, like maybe they need to change the timing on the light at different times of the day because the traffic is more or less. To do that, our first step is always going to be determine what our endpoints would be. What is the interval that we're going to be on? Well, in this case, it's pretty well defined that one day is 24 hours. So the least time would be at 0 hours, or right there at midnight, 12 a.m. Dog's making the shadow there. And the most time would be at 24 hours, so 24 hours in a day. So our interval is going to be from 0 to 24. Then our step 2 is going to be to see what critical values we have. So just like always for critical values, we're going to take the derivative. Slide that up there a little bit. Take the derivative, and then we're going to simplify that as much as we can. Set it equal to 0, and then find out, where is the numerator equal to 0? We don't need to worry about the denominator because the denominator can't equal 0. You gotta love a dog. This dog is about to be beaten because she's a big pain in the rear end here. The denominator, we don't care where the denominator equals 0. All right, clip 2. We don't care where the denominator is equal to 0 because that would make our whole function undefined. So we're not going to worry about that part at all. We are going to look at just taking our derivative, which happened to be a quotient up there, t over 0.1 t squared plus 10, and we'll use our quotient rule to derive. And when we do that, we have low d high minus high d low all over low squared. Bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So I take the derivative of that right here. Then I set that equal to 0. So I'm going to reduce just a little bit here just to make it a little bit easier. I distribute my 1. I'm not really worried about that. I combine my t squareds and things like that together, so I'm all set there. Then we're going to go ahead and say, okay, well, if that equals 0, I have 0.1 t squared plus 10 equals 0. So we just set the top equals 0. We solve to get t equals 10. I'm happy with that answer because it fell between my 0 and my 24, so that's perfect. If it falls between my interval, that's what numbers I'm looking for. So my first step, find the endpoints. My second step, derive, set the top equal to 0 if there even is a top and a bottom, and solve for my critical numbers. And then finally, I'm just going to evaluate the function at the critical numbers and at the endpoints. So I have t at 0, because that's one endpoint, t at 10, my critical number, and t at 24. I plug each of those into the original function, not the derivative, the original function. I want to know where that function is the highest. And when t is 0, I get 0. T of 10 is 0.5. T of 24 is 0.4. So the maximum number is 0.5. So 0.500 cars per hour pass through that at time 10. So since my clock told me I was starting at time midnight or 12 a.m., That means from 12 a.m., 10 hours later at 10 a.m. is when traffic would be the heaviest. So these optimization problems, sorry about that, are very simple. We are continuously going to take our equation. Sometimes they're going to give it to us. Sometimes, like our Farmer Fred problem we talked about there, it's just the area and perimeter. I know how much fence I have. When is the area maximized giving some constraint? And we'll look at some additional problems. There's some on Khan Academy we're going to look at. There are some with Calculus Maximus, and there's some notes for that you're going to look at as well. So use each of your tools wisely today. I am available again by text, so if you need me, go ahead and shoot me a text with specific questions or give me a call. We can try to figure out some of those as well. But the answer key is also attached. So if you are not sure, try those problems. Look at the answer key. See how we solved those problems. And it should be able to help you understand and recognize where you're going from there. If you have any other questions, though, let me know, and I will see you on Monday.